Welcome everybody to the Physics 211 Project 1, The Ball by Richard Dunninger, Daniel Giuliano, and Cooper Vaffi. Let's start by looking at the problem. We can see to the right we have a sphere with radius r and some charge around it. We also see that we have a 3D charge density given by the function P of r is equal to P naught times small r divided by big R. And in this problem, our goal is going to be to solve for the electric field and the voltage inside and outside of the ball. So we can start with some assumptions that we can make. We can use Gauss's law to solve for the electric field. We can assume there are no other charges inside or outside the sphere besides the ones given by the charge density formula. And the electric potential as r goes to infinity is 0. Now the reason we can use Gauss's law is because we're working with a sphere. With a sphere, we know that the area vector is always going to be perpendicular to the charge vector, or the field vector, apologies. So Gauss's law tells us two things. One, the net electric flux through any closed surface is equal to the charge enclosed by that surface divided by epsilon naught. And two, the electric flux inside of the Gaussian surface is governed by the charge inside of it. These two rules allow us to use Gauss's law to find the electric field at every point inside and outside of a ball. Due to the relationship between the electric field and the electric potential, we can find the electric potential by integrating the electric field.
Hello everybody, and welcome to the equations! Now, who doesn't love a good equation? Okay, so to begin, charge density. We were given the charge density as part of the equation. And again, just to reiterate, that is rho of r is equal to rho naught over little r over big R. And again, big R. That's the radius of the ball, and little r is basically anywhere between 0 and infinity. Okay, Gauss's law, as the lovely Daniel Giuliano said, because of the fact that it's a sphere, we can simply do the dot product of the electric field and the area vector. So we know that, again, because it's a sphere, we're never going to have a place where we're going to have a really weird dot product. We're never going to have a place where there's going to be 0 electric field. It's always going to be a dot product of 1. And that allows us to basically say that we can do Q enclosed over epsilon naught. Now, we're not given a Q charge. That would make things too easy. So we're given a density function. And now, we're going to integrate it to find our Q enclosed. But first, we must recognize that we have to use the surface area of a sphere, 4 pi big R squared, because that is the surface area of our sphere. So now, back to that beautiful, beautiful integral. So everybody remember Math 256? I do. That was something else. So basically, vector calculus tells us that we can use this specific kind of an integral, a spherical coordinate integral, to integrate our charge density function to find our Q enclosed, to then plug into our electric field equation. And so basically, we start out with 0 to 2 pi. So this is telling us that from 0 on the unit circle to 2 pi, we're going to have a complete circle, like horizontally. Now, 0 to pi vertically tells us that from 0 all the way down to pi, we're going to have a circle vertically. And then 0 to, in this case, big R, tells us that we're going to go from the 0 to the big R, which is the maximum radius, which is the radius of our sphere. And so, of course, then we can basically do rho naught r, little r over big R times r squared sine of phi dr d phi d theta. And this whole bit comes from the fact that it has to be a spherical coordinate integral. And so finally, we see that we have a super similar integral for the enclosed charge on the inside of the sphere, but you would be wrong if you thought it was exactly the same, because it's not. And the difference is that from 0 to little r. And basically what this is saying is that we're setting this up in a way where we can find the electric field, where we can have a function for the Q enclosed to then plug into the electric field for anywhere from 0 to infinity. It gives us the options to basically create Gaussian surfaces inside and outside the sphere. Okay then. So our potential difference setup. So basically, we integrated to find our Q enclosed, and we're going to plug it into the classic KQ over R hat direction, and of course KQ over R hat direction. And this allows us to now have a equation for the electric field of the inside and the outside of the Gaussian of the sphere. And so now, as you can see here, we have two special little integrals set up for our outside and inside potentials. So the first thing to preface is that electric field is a vector and potential is a scalar. So we're going to do for the outside potential, we're going to do the negative integral from infinity to little r, because we're basically saying that we're going from infinity back to r. So that's why, for instance, it's in the negative dr direction, because we're moving from the greater to the smaller and everywhere in between. And so we integrate our outside field function dotted with our negative dr, we're going to get our our potential equation. And now it's a very similar story for the inside. The difference being is that, first of all, as you can see, we have two integrals added together, but it's the same thing with the negative integral dotted with the negative vector, because again, it's going from the big to the little, from infinity to big R, so to the edge of the sphere, the initial sphere, and then from the big R to, well, little r, which could be anywhere, so that's why it's negative. And this basically allows us to set up an equation for the inside that accounts for both the outside and the inside potential. And so finally we get some answers. We made it, guys. We made it. And you didn't even see any of the ugly math involved because we're nice enough to not include it and because we get points docked off. So basically, as you can see, our friends, electric field of the inside, electric field of the outside, and now their new siblings, potential of the inside, say hello to everybody, and potential of the outside. And as you can see here, we have equations in terms of variables that work. These two are obviously the integrals that we set up, and this is the integral of what we set up. As you can see here, because we had to do a negative integral dotted with a negative, dr, we got positives. And basically now what we're going to do is we're going to sense make, and you're going to see how these just work. Let me turn over to my good friend Cooper Vaffy.
All right, sweet. So we have our answers set up, and let's do some sense making then. So first of all, let's start off with a unit check here. We are expecting an answer of newtons per coulombs for the E field and Newton meters per coulomb for the electric potential, as that is the E field just with a distance. So for our constants in the equation, we got K. We've been told this is Newton meters squared over coulomb squared. We also have our charge density equation, which we would expect to equal to coulombs per meters cubed for a sphere. And we have the equation right here. We can see that both radiuses are in the equation. Those will cancel out, leaving us with just the constant P naught. So we can see that P naught must have the units of coulombs per meters cubed. So we plug these constants into our equations, and trust me, we did it. We do get newtons per coulomb for the E field and Newton meters per coulomb for the voltage equation. For some special cases, we got the case where we set the Gaussian sphere at radius 0. So looking at the origin point, for the electric field, we plug in 0 for that little r there, we're going to get an electric field of 0. Now, we do have charges, positive charges surrounding the origin. However, all of these charges are equidistant and opposite, meaning the vector components will cancel out. This is different for the electric potential. We can see for the electric potential inside of the ball, we have a constant factor here that will remain there regardless of the radius. Let's get rid of that. Because the electric potential is not a vector, it is just a constant. So you add them up from all the charges, unlike the E field. For outside the ball, we can look at the case where the radius is infinity. When we get very far away from any charge, no matter how large the charge is, it's going to go to 0, the effect of the charge that it is, the force, electric field, electric potential, anything. And we do see that both of these equations for the E field and the electric potential have radius in the denominator. So plugging in infinity there, we get 0 for both of them, as we expect. We can also do some covariational reasoning on the other variables. Looking at the charge density, if we increase that constant P naught, we would expect the effect to amplify on both the electric field and voltage. And we do see that all the equations have a proportionality, like direct linear, that is. So we increase charge density, we're going to have a higher E field magnitude, higher electric potential. As for the radius of the ball, it's going to differ depending on whether we're looking inside or outside the charge ball. So if we're looking at the E field inside, we're going to increase the radius of the charge ball, and that will decrease the field because now the majority of the charge is further away from the point at which we're looking at. And this is opposite for the E field outside of the ball, where if we increase the radius of the ball, the charge is now getting closer to the outer realm, the radius we're plugging in. We can also look at an interesting case where both of our equations, we notice, have the domain of capital R, big R, the radius of the charge ball. So we can actually plug that into all of our equations, and we'll see we get the same answer for both E fields and both voltages. That is Kp naught pi capital R, or for the voltage, Kp naught pi R squared. All right, that's it for the sense making. I'm going to pass it back to Richard for some reflection.
Okay. Hello, everybody. Hello. Sorry. Basically, it's the best part of the physics project. It's reflection time. Okay, so as we look back on this wonderful, wonderful project, we can basically reference a few different things. So I decided to choose Get Ready Activity. We decided to choose Get Ready Activity 6, Lecture Week 3, and then like 2 others. But basically, Get Ready Activity 6, we're going to talk about Gauss's law and using Gauss's law. So these parts of the textbook, basically Gauss's law part just introduces us to the super basics, the dumb basics of Gauss's law, which is basically the enclosed charge is what's going to govern the electric field. And so we see different scenarios, like if it's a circle or a cube, and how those things will affect the dot product, because a cube will, for instance, have a more messier dot product compared to a circle due to the fact that not every E field vector and every area vector are perfectly, dot products of 1 or 0. And then using Gauss's law, now we can actually talk about a scenario where we're going to use a shape. And we used a very interesting scenario of an infinitely large sheet and a cube. And because that sheet is infinitely large, and because of the way the cube meshes with it, we're able to do a more simplified version of the electric field and the flux, but the flux is kind of irrelevant, because we know that the cube is going to have sections of area where the E field and the area are going to be dot products of 1, and where they're going to be dot products of 0. So it's very easy. And so now Lecture Week 3, Lecture 6, Exercise 1. If you don't remember Lecture 6, I mean, what are you even doing in this class? So basically, in this exercise, we talked about the very interesting case where we had an infinitely long wire and a cylinder around it. And if you notice, a lot of these cases depend on one part of it being infinitely long, which is an interesting variable to add. But this was similar to what we were doing, because now we're actually getting into something that has a circular component. It's not a ball, but it does have a circular component. So we can see how the circular side of the wire and the circular side of the cylinder will have a dot product of 1, and how the top and the bottom of the cylinder will have a dot product of 0, and that shows us that the field is radiating outward. And so now if we imagine this now, we bump it up to the more harder case of our actual project, we have charge everywhere, and we have dot products everywhere that are all 1. Finally, in conclusion, we've reached the end. Thank God. Round of applause. We survived. Okay, so due to all of our hard work, I feel we can end this presentation with one singular quote.
It just works.
Thank you, Todd Howard, our friend, Lord and Savior, and neighbor. Have a great night, everybody.